In today's video, we're going to go over finding the gradients of a couple activation functions. We're going to start with the ReLU function, which is actually pretty simple. So all it is we're going to go through these values I cannot type and talk at the same time. So we're just going to go through all these values and basically if what the ReLU itself does, the forward takes the inputs, and if they're less than 0, then you set the output to 0. And with that, basically you're kind of doing the same thing but backwards. If anything in those very same inputs are less than or equal to 0, you're going to set that gradient to 0 as well. So which actually makes me feel like ReLU activation is a very kind of maybe archaic, or not archaic, but I don't feel like it's a great linear or non-linearity due to the fact that you kind of zero out a lot of gradients, and it's also not very much of a non-linearity. I think it's just used a lot because it is so simple, it is very efficient to compute. And with neural nets, the whole hypothesis is if you have a bunch of, you have a big, well, theoretically infinite amount of linear combinations with non-linearities, you can derive basically any function. It's a close enough explanation. And that's all there is to it. If the input is less than or equal to 0, then the derivative that you're sending back to the previous layer is going to be equal to 0. And the next one we'll be doing is the sigmoids backward function. and actually have asked Gemini to explain the derivative. So we got here the sigmoid function, which is just 1 over 1 plus e to the negative x. And then the derivative of that is just the sigmoid function itself times 1 minus the sigmoid function. And that's it for the derivative, which we don't have to fully compute, since we already computed the sigmoid for each value here in the forward function, and this output is equal to the sigmoid. We can just skip a step and use the output as part of this equation. So we'll set each derivative of the input equal to that equation 1 minus, and since we already calculated up here what the sigmoid is and put it into the output, all we have to do is take that output value. So 1 minus that, times and we do have to, using the chain rule, we have to take this, multiply it by the d value, that the derivative value that's coming in from later on layers. And that's it. That right there is the derivative. Save that. And we'll go ahead and bring it in here. Okay, so we have the first layer. We'll do a ReLU. See up here. The constructor takes num samples, number of neurons. Num samples, number of neurons. Samples, num. We'll make a second layer so that we can use the sigmoid. And then we will round off with a sigmoid. Which takes number of samples and number of outputs. Which is number of neurons. Alright, so we go forward once. We'll do a ReLU of the first layer's output. Do the second layer. Oh yeah, dot forward. Second layer, we'll take in the output of the ReLU function, and then the sigmoid will take the output of the second layer. So that's the whole forward pass. And we'll go ahead and look at what the output of the sigmoid function is. And then we'll take the sigmoid backwards. We'll just take the sigmoid's output for now as the input to that. It'll really come from the, typically the input to this would be the derivative values coming from the loss function. So we got the sigmoid, and we'll do the second layer, taking in the sigmoid d inputs. And we got the ReLU, taking in the second layer's d inputs. And then take the ReLU's d input. ReLU's d inputs. Save it and print. So these are the outputs from the sigmoid function. Basically all the same right now. This here was the so we have the output of the sigmoid function, and then the, let's see, print. Double checking that that's right here. I guess we can check a couple more and see. Print that. We can also print the second layer's d inputs. So the ReLU's D inputs compared to the ones from the second layer. All right, so we have the output derivative of the second layer. This would be derivative of the ReLU function. Ah, yes, okay. I think I missed one piece. Okay, yeah, so these D inputs, that's not the whole story. I missed that. They're equal to the D values. They are equal to the D values. That's the wrong spot, sorry. I'm looking for the ReLU. Right here. So, D inputs are equal to the D values. These were just uninitialized values, is what was going on here. So, D inputs equal to the D values, but if the inputs were less than or equal to 0, you zero them out. All right, let's try this again. That looks better. And now we can check and see why are these all negative. Go back to the layer dense. And see, we've got the D biases and the D values, and the inputs times the D values. We get the derivative of the weights, but here we want the derivative here. We want the derivative of the inputs, which is the weights times the D values. So these times the weights will get you these. So if we go back here and we print the weights, save that. So we'll have, this is a much bigger number than this, times this negative, which is roughly the same as that. So you'll have a negative number. So that times that. So yeah, you'll get it. Well, these are both negative, so that'll be negative. That times that. But this is transposed. So it'll be more like that. So it'll be this times this. So negative 09 is bigger than 07, and 01 is bigger than 001. So this will be negative. Same for this, that times that be negative, and that is this one. All right, let's say we're looking for this number, which will be this times this, roughly the same. This is bigger than that, so it'll still be a slightly negative number. So yeah, makes sense. Yeah. And that's why starting out with this data set is really good, because you can actually go through these numbers here and check. Whereas if you are doing a more normal data set, such as MNIST, it's going to be the input is 28 by 28. So I think that's 700 numbers. And you do not want to check matrix multiples of that.